When our ancestors first invented numbers for counting crops and livestock, the concept of a number was exclusive to those so-called counting numbers. But as math progressively evolved, we expanded our definition. Numbers that represented geometric constants, numbers that represented nothing at all, or even numbers that represented something that is somehow less than nothing. The notion that these numbers should be elevated to the same status as counting numbers was absurd to many people, and those who believed in it were labeled as heretics. What started as a few points became an infinitely wide and infinitely deep continuous line, the number line. But who's to say that this one-dimensional object is really the end of the story? Maybe this line, which was itself an extension of points, could be extended into higher dimensions. Okay, that was admittedly a bit dramatic. Hi, my name is Basil Kiriakou, and I'd like to invite you to play just a simple game with me. The goal of this game is to see if we can extend numbers into some kind of two-dimensional object. If it works, we'll try three-dimensional objects and 4 dimensions and so on. To be explicit, what we want is to define rules of addition and multiplication that agree with the constraints of arithmetic. Just as any 2 points on a line can be added or multiplied to yield a new point, we expect the same behavior to work on a plane. As with the line, every point represents a unique number. To start, it may be helpful to use Cartesian coordinates, in which every position is labeled by 2 independent perpendicular elements, describing how far along each axis they are. Addition is created by adding points element-wise. For those of you familiar, this is effectively vector addition, where your points are represented as arrows that lead into each other, tip to tail. I think working with these arrows is easier in general, but the points are exactly the same. You can use either. Likewise, you may guess that multiplication can be performed element-wise, but that actually doesn't work. Here's an example. These are 2 non-zero points that multiply, quote-unquote, to 0. So this method does not satisfy our rules of arithmetic. But there is a way to multiply 2 numbers on the plane. The trick is to shift to radial coordinates, where every point is defined uniquely by an angle and the length from the origin. It turns out that if you take these lengths and angles, that you can create multiplication by multiplying the lengths and adding the angles. The resulting point satisfies the criteria for multiplication. And that's it. 2 definitions. One for multiplication, one for addition. We've successfully recreated numbers in 2 dimensions. But before we move on, let's play around with these for a little bit. One thing you might notice is that points on this x-axis here have a kind of attractive quality. Any points symmetrically above and below have equal and opposite angles, and thus when they're multiplied, they will collapse to the right-hand side. In fact, whether you're adding or multiplying, 2 points on this center line will never leave. After all, the y element is always going to 0, so 0 plus 0 is 0, and the angles that get added are always 0 or 180, which will always stay on this center line. The only thing that changes is whether you're on the right-hand or left-hand side. If one of your numbers is on the left-hand side, then it will stay on the left-hand side. Otherwise, it will be on the right, which coincidentally is the exact same behavior of the number line itself due to positive and negative numbers. If you play around with this, you'll notice that the behavior of these numbers is completely indistinguishable from numbers on the number line. And if 2 things are indistinguishable, they're the same thing. This is, in fact, the number line. And the plane here is an extension of it. Much like natural counting numbers were eventually extended to a whole line. For me, this property of negative numbers and multiplication, moving from one side of the number line to the other, was something I probably just accepted at a young age. I never really saw a justification for it, but this is one. The angle 180 plus itself will be 360, and it will return to the right-hand side. So if the center line is the number line, what's the rest of this plane? They're still numbers, but they feel weird, different somehow. It turns out you actually only have to add one extra number to your vocabulary to span the rest of the plane. That extra number is a number that rotates any other number by 90 degrees. I'm going to label it R for right angle number. You can find it right here at the point 0, 1. Since its size is 1, it won't distort under any multiplication. Just rotate. Now, every point can be expressed as a binomial, with its number line component and its rotational component. But the most exciting part is that the multiplication property we defined earlier is completely preserved, but you can multiply in the way you're used to. All you have to do is figure out what r squared is. Okay, well, multiplying by r turns anything 90 degrees, so multiplying by r twice is just 180 degrees. A little bit of math with trig identities, and indeed, these values are absolutely equal. Unfortunately, this value, which squares to -1, was not named by me. It was not called r. You may have seen it before as I, the imaginary number. When I first learned about I, it just struck me as this weird, almost ghostly thing. But I think that is because it's just taught in a really unfortunate way. The defining characteristic of I is that it rotates any number. The fact that it's the square root of -1 is simply a byproduct. And this rotation opens up the number line to an entire plane. It turns out that multiplication simply doesn't work in 3 dimensions. You can't define a way to multiply a set of 3 numbers such that all the rules of arithmetic are consistent. In fact, you can't do it in 3 dimensions or 4 or anything higher. This is it. This number plane is the whole story. And just like negative numbers, there are very real, very important problems that require this extension from just counting. So if you feel uncomfortable with the imaginary number, or thinking about numbers existing on a plane, I get it. It's still weird for me too. But I like to imagine how weird it would be for those ancient peoples to learn about negative numbers for the first time. That the product of 2 things less than nothing can just be a normal number. Maybe the only reason I don't find that weird is because I'm just used to it.